All right, so hopefully we can finish our proof of the inverse function theorem today. And in this first video, I just want to recap where we are so that we have all of the tools that we've put in place from previous portions of the proof ready to use for this portion. Okay, so here's what we have and here's what we need to prove. First, we have the assumptions that we're allowed for the sake of the theorem. We have a C1 function on an open set E, and it's a function of n variables with n outputs, the same n here and here. And A is a point in E where f prime of A is the identity. Remember, that was because we reduced the theorem to a special case where the derivative is the identity map. Then we defined a neighborhood of A called U so that these two things were provable. We were able to prove that the image of U is open and that restricting f to U gives you an injection and a bijection from U to the image of U, which we decided to call V. And in order to prove these two things, we used a tool which we will still need to use a little bit more, so I'm keeping the tool here. And that tool is this family of maps phi sub y. So for each n tuple, y, we define phi sub y, a function from E to Rn, like this. And the exact definition is not as important as, I guess, the property that it ended up having, which is phi sub y has x as a fixed point if and only if f of x equals y. So that is, we made use of that property to help us prove these two facts here about U. And to do that, we needed to know this fact about phi sub y, which we basically chose U to make this work. So the whole way that U was chosen to get everything else to work was it was chosen so that this happens. So that's where we used the continuity of f prime. We use the continuity of f prime to pick U so that this here happens. And what's left for us to prove, so if you remember in my statement of the inverse function theorem, I gave three conclusions, 1, 2, 3. And we proved 1 and 2. And what's left to prove is 3, which I've split up into these two components. First, we need to prove that so we know f restricted to U is this bijection, right? So it has an inverse. It's a bijection from U to V, so it has an inverse, which is from V to U. We need to prove that that's differentiable. And we also need to prove that the derivative is continuous. So the derivative is this kind of map. We need to prove that that's continuous. And then we will be done.